today we are going to learn a very important topic in analog VLSI design, which is differential amplifiers. Differential amplifiers are useful in analog CMOS design because they represent the input stage in operational amplifiers. Remember the op-amp from early circuit courses? We learned that op-amps have two inputs, and it takes the differential input and amplifies that differential input. So before we discuss the differential amplifiers and how they are built, let us review some basic concepts in circuit analysis. The first concept we will review today is what we call single-ended voltage. Basically, in single-ended voltage, the voltage is measured from one end or one node to ground. So if you look at this graph, for example, we have a voltage source connected to a resistor, and we are interested in measuring the voltage at this node to ground. This is a single-ended voltage. You're measuring voltage from one node to ground. On the other hand, double-ended voltage or differential voltage is the voltage measured across two ends or two nodes. So if you look at this circuit, for example, we have a voltage source V1 connected to a resistor R1 and a voltage source V2 connected to a resistor R2, and we are interested in the voltage between these two ends. That's the differential voltage. And you must pay attention to the polarity here. The polarity of the differential voltage VD states that the plus polarity is on the left hand side, so you have to pay attention to the polarity. But basically, if you will use KVL, you know that VD will equal to V1 minus V2. And remember that the current through the circuit is zero because it's open circuit, so the voltage at one end is V1 while the voltage at the other end is V2. Then VD is V1 minus V2. Another important concept in circuit analysis, and it could be new to you, but it is very important not only for the VLSI designers but also for the component level designers. Remember that the component level designers will use components such as the op-amps, and they have to understand some of the terminologies we cover in this course, such as the common mode voltage. The common mode voltage is basically the portion of the voltage that is common at both ends of the differential voltage. So, for example, I can say that V1 will equal to V common mode plus half of the differential voltage, V2 over V1, while V2 will equal to V common mode minus half of the differential voltage, VD over 2. And the physical interpretation of these equations is as follows. If you have a circuit like the circuit shown, you can see that we have V common mode at the bottom, and this V common mode is shared for both ends. So you can see that one end says that I have V common mode plus the voltage source here, which is VD over 2, and on the other side I have V common mode plus this voltage source, but this voltage source is minus VD over 2. And remember, the current is zero, so the voltage across the resistors is zero. Now, when you calculate VD, in this case, you know that VD will equal to V1 minus V2. And when you plug in the equations for V1 and V2, if you subtract V1 minus V2, you end up with VD, right? Because you have V common mode plus VD over 2 minus V common mode minus VD over 2. So this will give you VD. Now that we understand single-ended voltage, differential voltage, and the common mode voltage, let us have more notes on the differential voltage. Remember that this topic is about differential amplifiers, and to understand how differential amplifiers work, we must understand the concept of differential voltage. Basically, differential voltage supports single-ended voltage. And what do I mean here? Basically what I'm saying is if you have a differential voltage, you can use the differential voltage to describe a single-ended voltage. How can we do that? Well, the answer is very easy. Connect the other end to ground. If we have a circuit for the differential voltage, just connect the other end to ground. So if we connect V2 to ground, the other node will be ground, and all what we have is the differential voltage will read V1 minus 0, as you see in the circuit here, and basically VD is the same as V1. So now what we have is we were able to express a single-ended voltage using a differential voltage. And that makes sense. If you remember back in the old courses when we studied circuit analysis and we used to use the inverting configuration in the op-amp, what did we do? We ground the other end and now it becomes single-ended amplifier, right? So basically what you do, if you wanted to use a single-ended amplifier, just connect the other input to ground and you will have a single-ended voltage, right? Remember that basic op-amp circuit we had back in the old days? We know the op-amp uses differential input voltage, and by connecting one input to ground, we end up with a single-ended voltage. So we end up with a single input voltage at the inverting input, right? So this is something not totally new to us, but we are kind of refreshing our memory here. Now we are ready to introduce the concept of the differential amplifier. The question now is, what is the differential amplifier? The differential amplifier takes the differential voltage, the voltage difference at the input, and then amplifies the difference of the input voltage and sends it to the output. The output voltage may be single-ended, as in the op-amp, or it can be differential output. So if you see this configuration, this is a single-end output. It's basically a very simple op-amp circuit. You take the differential input and you send it to a single output, or it can be differential input, differential output. So it takes the differential input and then it sends it as a differential output. Both amplifiers are useful in many applications and analog IC designs, so we use both of them very frequent. The differential input voltage in the differential amplifier, remember we stress in the differential amplifier, the differential input voltage is the voltage difference between the two inputs, which are specified as VD will equal to V plus minus V minus, where the V plus is the voltage at the plus polarity and V minus is the voltage at the minus polarity. Basically, what it means is the differential input voltage will equal to the voltage across the input, or basically the voltage difference across the input. So here I have a question for you. What is the advantage of using differential input? Why we want to use differential amplifier? Why we wanted to amplify the differential input? The answer is very simple. Differential input voltage cancels the common mode input voltage, and it only amplifies the differential input. So there is many applications in electrical engineering to advance the speed of the IC circuits that requires us to take the differential input voltage. A classical example in something we call serializer deserializer circuit. The deserializer circuit is a special kind of circuit, usually communicates to the bus in the digital circuit. You see, we are discussing a very hot topic these days is a mixed signal design. What you do is you have, for example, a microprocessor would like to communicate with the memory, and the microprocessor communicates with the memory at very fast speed, that a lot of times we have a lot of noises surrounding that link between the microprocessor and memory. But what's important is the differential signals or the differential amplifiers are extremely important in advanced topics in analog IC design. By any means, what's the advantage of using the differential input? The advantage is that the differential input voltage cancels the common mode input voltage, and it only amplifies the differential input signal. That is why the differential amplifier is important. It cancels the common mode input voltage. Also, the common mode input voltage is the voltage that is common to both inputs. Remember, we discussed the common mode voltage earlier. We said it's the voltage that is common to both ends. Then the common mode input voltage is the voltage that is common to both inputs of the amplifier. The common mode input voltage may be an offset voltage to both inputs. That can be the DC offset to bias the transistor, for example. So what we can say is the voltage at the minus terminal will equal to V1 plus V offset, and the voltage at the plus terminal will equal to V2 plus V offset. So the offset voltage is common for both inputs, the plus and the minus. Then we can say that the differential input voltage VD will equal to V plus minus V minus. So this will equal to V2 plus V offset minus V1 plus V offset. And the V offsets cancel each other out. So we have VD equal to V2 minus V1. In this picture, it shows you that the voltage at the plus polarity will equal V2 plus V common mode, and the voltage at the minus polarity will equal to V1 plus the common mode. And when you do the differential voltage, you can see that the differential voltage is basically V2 minus V1. So the common mode input voltage can be generated by noise of other components in the circuit. So now what we can say is the V plus will equal to V2 plus V noise, and V minus will equal to V1 plus V noise. And by taking the differential input voltage, we can say that V2 plus V noise minus V1 plus V noise, and the V noise cancel each other out. Remember that noise is common voltage to both inputs, so the noise is cancelled, and what remains at the input is the difference between the two input voltages. Now the differential input voltage is V2 minus V1. There is two types of noises that are eliminated by the differential amplifier. The first one is what we call the power supply noise. The power supply creates a lot of noise in the circuit for many reasons, and you would like to cancel that noise. That noise will be common to both inputs because that noise comes from the power supply. So you'll be able to cancel the power supply noise by using differential inputs. The other one is through electromagnetic interference. We call it EMI. So the electromagnetic interference noise is created by inducing the magnetic field between adjacent components, and the differential amplifier will be able to cancel that electromagnetic interference noise. Remember, we said that by Ampere's law, if there is a current flowing into a conductor, that current will create a magnetic field. If this current is changing, because a lot of times we use digital circuits, and the digital circuits are adjacent to the analog circuits, and they are clocked, so they go up and down, so the current is changing, and that change in current will be induced as a voltage by Faraday's law. So Ampere's law says that if there is a current flowing through an inductor, it will create a magnetic field. If that current is changing, according to Faraday's law, it will be induced in adjacent conductors due to the magnetic field. And we would like to eliminate that noise through differential amplifiers. Also, another important note that we also stated it earlier, differential amplifiers may implement single input amplifiers by grounding the other input. So this is also commonly used as before. When we show you here in the graph for this differential amplifier, you can ground one input and then the other input will be the differential input. Basically the input to the amplifier, which is VD, in this particular case will be V1, because V1 minus 0 is V1. So you can implement a single input amplifier using differential amplifiers. Now we are interested in what goes on inside the differential amplifier at the transistors level. So the topic is basic transistor level CMOS differential amplifier. To show you that, we have to go back to the single stage amplifier. So we have to look at the single-ended common source amplifier. So basically we have one input, one output of the basic common source amplifier. So here is the circuit. As you see, we have the transistor M1 where it has V1 is coming into the gate, and then we have RD at the drain, and the gain of this amplifier was evaluated in earlier lectures to be minus GM times RD in parallel with RO. In this particular circuit, we assume the DC biasing is taken care of. We are not going to worry about the DC biasing, so it is something that is taken care of. Also, remember that the output voltage for the common source amplifier has two components, DC component and AC component. So let us state that the output voltage contains the DC and the AC components. Now the DC component is easily evaluated. Vout1 is equal to VDD minus ID times RD. And watch out for the logic here. What happens is if the transistor is on, if the DC component of the transistor is on, that means the drain current is going down and the drain current flows through RD. That means by Ohm's law there is a voltage drop across RD. Then we say that the voltage at the output will equal to VDD minus the voltage drop across the resistor, which is ID times RD. And this intuition is very important for analog engineers. I would like you to master it if you have not mastered it in early courses in electronics. Make sure you master it and visualize it. The DC voltage at the output will equal to VDD minus the voltage drop across the resistor, which is ID times RD, where ID here is the DC voltage. So everything we say in here is the DC voltage. Then we can substitute for the expression of the DC current. Then the output voltage Vout1 will equal to VDD minus 1/2 KN W L times VGS minus VT quantity squared multiplied by 1 plus lambda times VDS. This component here is the DC current for the transistor multiplied by RD, and that will be the DC voltage at the output. We did this analysis in earlier lectures when we discussed the single stage amplifier, and we also know the small signal AC gain is given as Vout over V1 will equal to A, which is the AC gain, and that will equal to minus GM times RD in parallel with RO. So this is a review of the single stage common source amplifier. However, we are interested in the differential amplifier. So how is the differential amplifier is implemented? Well, the differential amplifier is implemented using two identical common source amplifiers. So we will have two common source amplifiers as shown in the figure here. This amplifier has transistor M1 and this amplifier has transistor M2. And in addition, we have the two inputs V1 and V2 that will go to each amplifier. Here is the trick of the circuit. Watch out, it's very clever. If each stage has the same DC biasing, then the output DC voltages of both stages are equal. What that means is, if we made sure that all the components are identical, that means the two amplifiers are identical, then the DC voltage of both amplifiers at the same location is equal. Basically, the DC voltage at the gate is the same and the DC voltage at the outputs is the same. So the DC voltages are equal for both stages. But the differential output voltage is the voltage difference across both outputs. To simplify the conception here, we're going to say that the differential output voltage is the AC signal. It doesn't have to be, but we're going to stress it here to be the AC signal. Then the differential output voltage, which is the AC signal here, is the voltage difference across both outputs. Then the output voltage, Vout, is defined to be Vout2 minus Vout1. I defined it here to be Vout2 minus Vout1. But we know that Vout2 is basically nothing but minus Gm times Rd in parallel with Ro times V2. How did I get that? Well, because this circuit is a single stage common source amplifier, then we know the output voltage is basically the AC gain, which is minus Gm Rd in parallel with Ro, times the input voltage, which is V2. And the same thing for Vout2, so we're going to say minus Gm times Rd in parallel with Ro multiplied by V1. So now we define the AC output voltage to be Vout2 minus Vout1. And when we substitute it for the AC output voltage is Vout2 minus Vout1, that's what we have. But because the two transistors are identical, that means GM1 and GM2 are the same, which are Gm here, and Rd and Ro are the same because the two amplifiers are identical, then we can really factor Gm Rd in parallel with Ro out. So what we will have is Vout will equal to minus Gm times Rd in parallel with Ro times V2 minus V1. And this is interesting because V2 minus V1 is nothing but the differential voltage. So now we can say that Vout, which is the differential output voltage, will equal to minus Gm times Rd in parallel with Ro times the differential input voltage Vd. And that is what is exciting. Now we find the differential output voltage in terms of the differential input voltage. And that is the basic structure of the differential amplifier. Let us have notes about the differential amplifier. Here is the first one. The two transistors M1 and M2 must be in the saturation region and conducting at all times. The question is why? The answer is very simple. In the saturation region, the two transistors are behaving as amplifiers. To use the circuit as amplifier, transistors have to be in the saturation region. This way, for small voltage in VGS leads to a large current in ID, which gives you a larger voltage gain. right? That's the basic concept of amplifier as we discussed it in earlier lectures, that you have to make sure that the transistors are in the saturation region. Otherwise, the circuit does not behave as good amplifier and the output signal become distorted and nonlinear. Here is the second note. Vout1 and Vout2 must be less than VDD at all times. Otherwise, the signal clips. And that is a problem. Now the question is why the signal will clip. We discussed this before. The signal will clip because the current through the drain of the transistor must always go down, otherwise the transistor will be off. That means the voltage at the drain has to be lower than the voltage at VDD so that the current through the resistor RD will flow down by Ohm's law. You see why? Otherwise, current through the resistor will be zero because the transistor prevents the current from flowing up. You see, so Vout will clip if Vout1 or Vout2 is higher than VDD. It cannot get any higher than VDD. Here is the third note. Vout1 and Vout2 must be greater than VGS minus the threshold voltage so that neither transistor moves to the triode region. Right? Because VDS must be greater than VGS minus the threshold voltage. That's the condition of saturation. This has to be true at all times. Here is the next note. In general, biasing both transistors using one current source is used in practice. So the way we bias this circuit is we use one current source as shown in the circuit here. So in this circuit you can see that the source of M1 and M2 are connected together into one current source. Since both transistors are identical, the same DC current flows through both transistors. Also, the DC output voltages of both transistors are equal. The reason is because both DC currents through both transistors are the same, and these two currents will flow through RD. That means the DC voltages at the output are equal. So the question is, how do we implement this current source? Well, the implementation of the current source is very easy to do. The way we do it is the current source is implemented using one single transistor. Basically, the current source is a transistor that is properly biased to give ISS. We can show you here in the circuit that here is the transistor M3, which is biased at a particular voltage such that ISS will flow through this transistor. We called it M3, and because the two transistors are identical, and if the DC components of V1 and V2 are equal, so the DC components are equal, they must be equal, then the currents will flow equally through M1 and M2, and we call them here to be ISS over 2 that will flow through M1 and ISS over 2 that is also will flow through M2. So the same DC bias and current will flow through these two transistors. They will merge together and they will give us IS to flow through V bias. Now we would like to have a better understanding of what goes on inside the differential amplifier. So let us develop intuitive analysis of the behavior of the differential amplifier. So we are still at the intuitive level, We are not developing any mathematical equations yet. We just wanted to understand intuitively how is this particular amplifier work. So the question is, how does the differential amplifier work? The idea here is, how would it amplify the signals? Let us just look at it intuitively. Let's see how does it work. So here is the first case. What happens if V1 and V2 are equal? If V1 and V2 are equal, the source of M1 and M2 is the same. Then VGS1 and VGS2 are the same, which leads to I1 equals to I2, which leads to Vout1 equals to Vout2. Then the differential output Vout is 0. You see? So this is a very important remark. Look at it again. Let's look at it again and look at it quick. If V1 equals to V2, then VGS1 is the same as VGS2. Then the current through M1 is equal to the current through M2. Then the same output voltages at both transistors are equal. Vout1 equals to Vout2. Then the differential output is 0. So if the differential input is 0, if V1 equals to V2, then Vout equals to V2 and the differential voltage is equal. Here is the second condition. What happens if V1 is greater than V2? So now we're saying that the voltage for the input 1 is bigger than the voltage for input 2. What happens? Then VGS1 is bigger than VGS2. That means ID1, which is the current through M1, is bigger than the current through M2. You see that? That means the voltage Vout1 is less than the voltage at Vout2. The question is why? You see, watch the trick. If V1 is bigger than V2, then Vout1 is smaller than Vout2. Why is that? Because if the current through M1 is bigger than the current through M2, there will be more voltage drop across the resistor of M1 than the voltage drop across the resistor of M2. You see, the voltage drop across the resistor of M1 is bigger than the voltage drop of the resistor at M2. That means VO1 is less than VO2. See, and that's very interesting. That means Vout is positive the way we defined it, because we defined Vout to be Vout2 minus Vout1. Now here is another case. What if V1 is much bigger than V2? Under this condition, we can say that ID1 will be much bigger than ID2. That we can say that ID1 approximately will equal to the biasing current ISS. Or we can say that the current through M2 is basically 0, right? Because VGS1 is much bigger than VGS2, then the current through I1 is so large that it takes all of the bias current ISS. Under this condition, Vout2 will be VDD and Vout1 will be roughly 0. And you have to make sure that all transistors are saturated. If the transistors are not saturated, this will not work. The output signal will be distorted. So that's a requirement that you carry with you all the way through when you design amplifiers and CMOS technology. Transistors have to be in the saturation region. There is another important note, and this important note is about this transistor, the biasing transistor M3. Note that the drain of M3, which is D3, is the same as the source of M1 and M2. That means VD3 equals to VS2 will equal to VS1, but we also know that M3 must always be saturated, right? Because if it's not saturated, the circuit will not work as nice. And it will have other problems that we will discuss later. The question now, what is the effect of the V common mode on M3 in the circuit? Well, here is the trick. Since VGS1 and VGS2 are greater than the threshold voltage for that transistor, that's for both transistors to be conducting. Remember, VGS must be greater than V threshold voltage. Otherwise, we don't have enough voltage to conduct, right? So both transistors have to be greater than the threshold voltage to be conducting, and VDS must be greater than 0 to be conducting. Then V common mode at the input must be greater than the threshold voltage in this particular circuit. So there is a strict requirement in what's the minimum input voltage at the input stage of the differential amplifier. Here is another question. What if the source of M3 is connected to another voltage like VSS? So remember that when we use op amps, we say that the power supply of the op amp can be VDD and minus VEE, right? So it can be plus 15 and minus 15. So that source will be at the bottom of M3, at the source of M3, right? The negative voltage, the negative biasing voltage will be at the bottom of M3. So under this condition, we know that V common mode has to be greater than V threshold voltage plus VSS for both transistors to be on. And also we know that V common mode has to be less than VD plus the threshold voltage at all times for both transistors to be in the saturation region. So in summary, what I'm telling you here is the common mode input voltage is bounded from the top and from the bottom. So the transistor remains conducting and in the saturation region at all times. You see, and that is very important. The common mode input voltage to the differential amplifier is very important. How high can we go must be limited so that both transistors are in the saturation region, and how low can we go must be limited so that the bias and current through the circuit is not affected as much. Before we introduce the analytical mathematical derivation for the gain, let us define the differential gain. The differential gain is defined as the differential output over the differential input. So we can say A, which is the differential gain, is equal to the partial derivative of V out, which is the differential output voltage, over the differential input alpha VD. So alpha V out over alpha VD is the differential gain, but we know that the output voltage is Vout2 minus Vout1. Then we can say that the differential gain is defined as alpha Vout2 minus Vout1 over the differential input, which is alpha of Vn2 minus Vn1. So this is the mathematical definition of differential gain. Basically, what that means is if we change the differential input voltage, the differential output voltage should also change. Now the ratio of the differential output voltage over the differential input voltage is the differential gain. So how much the output changes relative to the change in the input is the differential gain. Now we are ready to do the analytical, which means mathematical, derivation of the differential gain. Now there is two major methods that are used to define the differential gain. One is called the large signal analysis, and the other one is the small signal analysis, or the AC gain. So let's look at method 1, which is the large signal analysis. Basically, the differential gain is defined using the transistor's current equations. And for simplicity, we will assume lambda, which is the channel modulation index, to be 0. So we know the results here is approximated. In fact, as technology advances and the transistor feature size gets smaller and smaller, lambda becomes more dominant. And other important parameters, such as the tunneling of the gate, which means that the CMOS start to behave as a bipolar transistor because there will be a current flowing through the gate. That current becomes very large nowadays for the digital circuits. The analog circuits still use bigger feature size, so they are not as problematic as the digital circuits. Some of the challenges today arise when we use mixed signal design. When we interface digital circuits with analog circuits in the same IC chip, because nowadays everybody uses system on chip to reduce cost, which means that analog circuits are built adjacent to digital circuits on the same wafer, so there will be problems that arise. And there is few companies who are leaders in this technology, and many of these companies provide fabless manufacturing, which means that they will do the design and then send it to the companies who will do the fabrication. These terms are very important nowadays in Silicon Valley and around the globe, where people would like to design circuits on the computer only, and they sell it to customers. So customers can go and fabricate these circuits. And there is numerous companies that you can refer to based on your preference. To go back to our topic here, we are interested in defining the differential gain using large signals, which means the transistor's current equations. So we know that the output voltage Vout1 for transistor 1 will equal to VDD minus ID1 times RD. And we also know that VO2 will equal to VDD minus ID2 times RD. Now keep in mind that this is for all voltages and currents, the AC signal and the DC signal together. We call it the large signal analysis. This is the overall equation. Then we can define delta V out here. So let's pay attention to the definition. Delta V out to equal to Vout2 minus Vout1. This is basically the differential output voltage, right? So delta V out is basically Vout2 minus Vout1. Then we can say that delta V out will equal to Vout2 minus Vout1, which is basically ID2 minus ID1 times RD. We substituted for Vout2 and Vout1 in the delta V out equation, and the VDD terms cancels out. Remember, the condition is VD is not 0, which means V1 doesn't equal V2. That means I1 is not equal to I2. It doesn't have to be. Then we can say that let delta ID to equal to ID2 minus ID1. Then delta V out will equal to delta ID times RD. I substituted for ID2 minus ID1 in terms of delta ID. That's all what we did. Now we would like to define the differential input delta Vn to equal to Vn2 minus Vn1. Then the differential gain is given as alpha of delta V out over alpha of delta Vn, and that will equal to alpha of delta ID over alpha of delta Vn times Rd. All what I did here is I substituted for delta V out to equal to delta ID times RD. But also we know that the source Vs is the same for both transistors. Since Vs is the same for both transistors, then we can say that Vn2 minus Vn1, which is basically the differential input voltage delta Vn, is nothing but VGS2 minus VGS1, because the sources are the same. And we also know from the current equation, VGS minus the threshold voltage quantity squared will equal to ID over 1/2 mu n COX times W over L from the current equation. Now we can solve for VGS, so we can say that or VGS will equal to the square root of ID over 1/2 mu n COX W over L, and then add the threshold voltage to it. Now this is the trick. Since Vn2 minus Vn1, the differential input voltage, is the same as VGS2 minus VGS1, then we can say that Vn2 minus Vn1 will equal to, now we're going to substitute for VGS2 in terms of the square root equation. This will equal to the square root of ID2 over 1/2 mu n COX W over L minus the square root of ID1 over 1/2 mu n COX W over L, and the threshold voltage is cancelled out because I have the threshold voltage of VGS1 cancels the threshold voltage of VGS2. Now I can take the partial derivative of delta ID with respect to delta Vn, which is nothing but the partial derivative of ID1 minus ID2 over the partial of Vn1 minus Vn2. Now take the partial derivative explicitly and then do some algebra. So after some algebra we get alpha delta ID over alpha delta Vn will equal to 1/2 mu n COX W over L times 4 times ISS over mu n COX W over L minus 2 times delta Vn over the square root of 4 ISS over mu n COX W over L minus delta Vn squared. Now remember that this is the large signal, right? Now what we're going to do is we're going to have this explicit condition. We will say that we are interested in the large signal analysis, but we're going to start with the DC component. So we're going to say that delta Vn DC equals 0. What you do here is we're saying that the large signal analysis force the delta Vn to be 0, then the differential gain will equal to alpha delta ID over alpha delta Vn at delta Vn equals 0 at this DC biasing condition times RD, and that basically will equal to the square root of mu n COX W over L times ISS times RD, whereas ISS here is the biasing current, which is ID1 plus ID2. Then the gain may be expressed as Gm, which is here Gm is the transconductance of the amplifier times the output resistance RD. And that is basically the square root of mu n COX W over L times ISS times RD, where the transconductance of the amplifier, which is Gm, is equal to the square root of mu n COX W over L times ISS. Here is the summary of the large signal derivation. here is the first point. If the two half circuits are identical and the DC gate voltages are identical, that means the DC VN1 equals to the DC VN2, then the differential DC output voltage is 0. Make sure that this is the DC differential output voltage. If the input differential voltage is not 0, then the differential input voltage is amplified at the output. So let's show you a graphical representation of what's going on here. Let's the horizontal axis to be the delta VN axis, and the vertical axis, which is the delta ID axis, is basically ID1 minus ID2. What we realized is if delta VN is more negative, then ID2 will be bigger than ID1. And by making delta VN negative, we start to realize that the current ID2 minus ID1 start to reach saturation toward ISS, which means that all of the current that flowing from the biasing current source will be supplying the transistor M2. And if delta VN is more negative, we start to realize that most of the current will go through ID1, and the current through M1 will increase by increasing delta VN until we eventually reach ISS. The second method to come up with the differential gain of the amplifier is to use the small signal analysis. So basically we find the AC gain of the differential amplifier. There are three approaches which lead to the same answer. The first approach, which we will cover next, is called by superposition. So basically what we do is we apply VN1 and kill VN2, solve for the output voltages Vx and Vy due to VN1, then kill VN1 and apply VN2 and solve for Vx and Vy due to VN2. The first thing we're going to do is we're going to kill VN2, so we short it to ground, so the circuit will look like this. And now, as you see here, we have applied V1 and we have killed V2, and we are interested in the AC signal analysis. So basically what that means is the current source becomes open circuit, and now we can analyze the circuit using AC signals. So one of the things we'll be looking at is we would like to see what's the equivalent resistance seen at the source of M1. Basically we will look outside the source of M1, which is basically looking into the source of M2. And we know from previous lectures that when we look into the source of a transistor, we see 1 over Gm. The source resistance looking into M2, which is looking out of M1, is Rs, and that will equal to 1 over Gm2. Then the equivalent circuit becomes easier. What we have now is Vn connected to the transistor, and then at the drain we have Rd1, and here is Vx. And then at the source of M1, its equivalent circuit is 1 over Gm2. Now we can solve for the voltage Vx due to V1. We can solve for Vx very easily because the circuit is common source amplifier with a degenerated resistor in the source. We know the output voltage of the circuit, which is Vx due to V1. So that basically minus the top resistance over the bottom resistance times the input voltage. So that is minus RD1 over 1 over GM1 plus 1 over GM2 times VN1. So that is easy to solve for. Now the question is, how would we find Vy due to V1? Vy due to V1 is a little bit tricky. The way we're gonna do it, we will Thevenize M1 into one voltage source and one equivalent resistance, and then we can solve for the circuit. So the way the circuit will look like is we will have a Thevenin voltage source connected to our Thevenin, and then we will have the source of M2, and then we have M2 connected to RD2 connected to the power supply. And keep in mind that we are doing AC circuit analysis. Basically, to find a portion of Vy that is caused by Vn1, we Thevenize M1, and then M2 becomes common gate amplifier. When you solve for our Thevenin becomes 1 over Gm, and that makes sense because when you look back into the source of M1, you see 1 over GM1, and we also know that the gain from the gate to the source is unity if the output resistance is open circuit, right? So these are by inspection. Remember, Thevenin circuit says disconnect the load, so you disconnect M2, and then we're going to look at the output resistance. The output resistance into the source is basically 1 over Gm, and the gain from the gate to the source is unity if the output resistance is 0, if the output resistance is infinity, and lambda is 0. So basically our Thevenin is 1 over Gm1, and the Thevenin voltage is Vn1. Now we can solve for Vy very easily. So Vy is the top resistance over the bottom resistance times the input voltage. So we can say that Vy1 is equal to RD2 over 1 over Gm1 plus 1 over Gm2 times Vn. So we can say now Vy minus Vx, which is the differential output voltage due to Vn1, is equal to 2 times Rd over 1 over Gm1 plus 1 over Gm2 times Vn1, and we know that Gm1 equals to Gm2 and Rd1 equals to Rd2, then we can say that Vy minus Vx due to Vn1 is basically Gm times Rd times Vn. And by similar analysis, we can say that Vy minus Vx due to Vn2 is basically minus Gm Rd times Vn2. And by adding the two equations together, we can say now Vy minus Vx due to Vn plus Vy minus Vx due to V2 is basically Gm times Rd times Vn minus Gm times Rd times Vn1 minus Gm times Rd times Vn2. And now by factoring out the Gm times Rd term and dividing by the differential input, we say that the differential gain, which is Vy minus Vx over Vn1 minus Vn2, will equal to Gm times Rd. And this is here is differential gain for differential amplifier. The second method for solving of the AC gain is to use what we call the half circuit symmetry. So basically the differential amplifier is broken into two circuits and they are symmetric each circuit is called half circuit, so we call it half circuit symmetry, which means that if we solved for one portion of the circuit, we can solve for the other portion of the circuit as well. So you only need to solve for one circuit, then you will be able to solve for the second circuit. So in order for us to do that, we have to make some assumptions. Let us make the first assumption. If the two transistors are symmetric and Vn1 is increased by a factor of delta over 2, while Vn2 is decreased by a factor of delta over 2. Ideally, Vn1 should equal to Vn2, that's the DC bias condition, but if we have some differential voltage difference, we're going to say that half of the voltage will go up in V1 while the other half of the voltage will go down in V2. Then we can say that Vn1 will equal to V common mode, this is the DC voltage, plus delta over 2, and Vn2 is basically the V common mode minus delta over 2. Under these two conditions, we can state that the differential input voltage is given as Vn1 minus Vn2 will equal to delta. So over here we defined Vn1 minus Vn2, that equals to delta, which is the differential voltage of the input. Under this condition, Vp, which is the voltage at the source, doesn't change. So, and this is critical to the derivation of the half circuit. So what we are saying is the following. Half of the differential voltage increased in the first circuit, while the other half of the differential voltage is decreased in the second circuit. If that happened, then the voltage at the source, we calling it Vp here, doesn't change. It's gonna remain constant. Then the AC signal at the source of M1 and M2 is 0. That means there is no AC voltage at that particular point, and the source of the AC circuit is grounded. So we can assume that the source of M1 and the source of M2 in the AC circuit is connected to ground. This is very critical. As a result, the circuit is simplified into two common source amplifiers as shown in the figure here. So as you see in the figure, we have the two resistors R1 and R2 connected to the two transistors M1 and M2, and then over here we have the two input voltages V1 and V2. So now we are interested in the differential gain. So to solve for the differential gain, we got to evaluate Vout1 first and then Vout2, and then we take the difference, and we will be able to come up with the expression for the differential gain. So what we can say is Vout1 will equal to minus Gm times Rd times Vn1, but we already defined the expression for Vn1 to be V common mode plus delta over 2. Then we can say that this will equal to minus Gm times Rd times V common mode plus delta over 2. And the same thing we can do for Vout2. Then we can say that Vout2 will equal to minus Gm times Rd times Vn2, and I will substitute for Vn2 to be V common mode minus delta over 2. So this will equal to minus Gm times Rd times V common mode minus delta over 2. And we already know the differential output voltage be the difference between the two terms, so which is Vout2 minus Vout1. And when we carry the math, this will equal to minus Gm Rd times Vn2 minus Vn1, and the V common mode terms cancel out. And by dividing by Vn2 minus Vn1, we have Vout2 minus Vout1 over Vn2 minus Vn1 to equal to minus Gm times Rd. We end up with the same answer as we did using the superposition technique. The following statement is very important, and it is proven in the literature. so we will skip the proof. Here is the statement. Any two input signals may be divided into two portions, the common mode portion and the differential portion. That can be expressed as Vn1 will equal to V common mode plus delta over 2, and Vn2 can be equal to V common mode minus delta over 2. Such that to evaluate the V common mode, we can say that Vn1 plus Vn2 over 2, and the differential input voltage here is delta will be Vn1 minus Vn2. This statement is extremely important. Basically what it says is if I wanted to find the differential voltage, I simply take the difference. But if I wanted to take the common mode voltage, I add the two signals and I divide by 2. So make sure that we have the common mode voltage is evaluated by taking the average of the two input signals, and the differential voltage is evaluated by taking the difference of the two input voltages. This is extremely important remark. Make sure you keep this thought with you whenever you deal with the differential and the common mode voltages. The next topic, which is an exciting topic that we will discuss today, is called the common mode response. And basically it says that how is the differential amplifier response or behave in terms of the common mode voltage. Remember, the common mode voltage doesn't have to be DC. It can be due to noise or electromagnetic interference. So it can be AC signal as well. It can be small AC signal, but it is common to both inputs of the amplifier. So the first condition we're going to study is what happened if we have a common mode input voltage but for perfectly matched differential amplifier. What happens to the common mode signal? How will the amplifier respond to that common mode signal? To show you how is the differential amplifier behaves, we're going to assume the following. We're going to say that here is the circuit. We have VDD, we have RD, then we have the Vout1 and Vout2, which are connected to the transistors M1 and M2, which are connected to the input voltages, and the sources are connected together, but they are connected to a resistor. We're going to call it RSS. That resistor is the equivalent resistor of the transistor, for example, or it can be just a biasing resistor, and the V common mode voltage determines how much current will flow through this resistor. So over here we found the equivalent resistance of the transistor looking into the drain, or we have inserted a resistor at the source. By any means, there is an equivalent resistance at the source of M1 and M2. Then what we can do is we can find one equivalent half circuit for this amplifier. How are we going to get the equivalent half circuit? You have to keep in mind that this circuit is perfectly matched, which means that the voltage at the drains are the same, the voltages at the sources are the same, and the voltages at the gates are the same. Then we can combine these two transistors into one transistor, because it seems that every node in the two transistors have the same voltages. Then we will have a half circuit equivalent circuit for the common mode. Keep in mind that this half circuit is for the common mode circuit. The common mode half circuit says that we're going to have RD in parallel with RD, so from the top we will have 0.5 RD, because the two nodes of the resistors have the same voltages, so you can assume they are parallel. And then this resistor is connected to a transistor, where the transistor is the two transistors in parallel. So basically this equivalent transistor will have twice the width but the same length channel. So this transistor will have twice the transconductance, 2 times GM, right? And then we'll have the equivalent resistance at the bottom, which is RSS, and the gate is connected to the common mode voltage. So basically what we're saying is this differential amplifier, when it comes to the common mode voltage, we are stressing the common mode input voltage, this amplifier has one equivalent half circuit, and the two transistors will behave in parallel, and this will be the equivalent circuit. So this particular circuit is nothing but an amplifier. It's a common source amplifier with a degenerated resistance. Then the common mode voltage will be amplified at the output, and it will have the same voltage at both ends, right? Vout1 and Vout2 will have the same common mode voltage as the common mode voltage at the gates of M1 and M2. Vout1 and Vout2 voltages will also swing. Then we can say that the common mode voltage gain, we're going to call it AV common mode, will equal to Vx, which is the output voltage at the drain of this parallel transistor, over Vin common mode. And we know the gain for this amplifier is nothing but the top resistance over the bottom resistance. Then we can say that AV common mode, the gain for the common mode, will equal to minus the top resistance, which is RD over 2, over the bottom resistance, which is 1 over 2 times GM plus RSS. Keep in mind that the transconductance of this new transistor is twice the transconductance of M1 or M2. That's why you have 1 over 2 times GM. It's twice the transconductance because the transistors are in parallel. So what we have said so far is that if we have a common mode input voltage and the circuit is exactly matched, then this common mode voltage, if it's AC, it will swing at the output. So we will see the same common mode voltage swings at the output. One will have it and Vout2 will have it, which is something that makes sense. Now we know how much the voltage will swing due to the common mode input voltage if the circuit is exactly matched. Now, another condition that we are interested in is what happens if the differential amplifier is not fully symmetric. For example, the first case, if RD1 doesn't equal RD2. When we fabricate these circuits, we will have deviations from the desired values. So it's not going to be, for example, 1 mega ohm resistance, it will deviate by %, right? So that's something we have to live with. So now what happens if RD1 doesn't equal to RD2? That happens due to the tolerance of the fabrication process, for example. So what we're going to say is let the resistor of M1 to be RD and the resistor for M2 to be RD plus delta RD. So basically what we're saying is one resistor is perfectly matched while the other resistor is deviated by delta RD. It doesn't matter which one higher, which one lower, right? So you can always select the lowest value will be the actual value and the higher value deviated by delta RD. We can break this circuit into two half circuits very easily. If you will look into this resistor RSS, we know that this resistor RSS has a voltage across it called VB, and also the current through it is the current coming from both transistors, where each transistor has ISS over 2. So by breaking the circuit into two half circuits, we can see that the first half circuit will have a resistance equivalent of 2 times RSS, and the second circuit will also have an equivalent resistance of 2 times RSS. Note that the voltage at the source of each transistor will be VP, then the current going through each half circuit through the bottom resistor is ISS over 2. So that's why when we break the circuit into two half circuits, we get the resistance to be twice as much because the current through each half circuit is half as much. So let's assume delta V common mode be the change in the common mode input voltage. Then we know the M1 circuit behaves as common source amplifier with degenerated resistance. Then we can say that Vout1 will equal to minus delta V common mode times GM-RD over 1 plus 2 GM times RSS. Also, the output voltage at V2 will equal to minus V common mode times GM times RD plus delta RD over 1 plus 2 times GM RSS. And the output differential voltage is given as the difference between Vout1 and Vout2. So we say that Vout1 minus Vout2 will equal to delta V common mode times GM times delta RD over 1 plus 2 GM times RSS. And basically the GM-RD on top cancels out for both terms. Now we can define the common mode differential gain due to the mismatch in RD to be A common mode to equal to Vout1 minus Vout2 over delta V common mode, and that will equal to GM times delta RD over 1 plus 2 times GM times RSS. The common mode can also be affected by the change in the transistor's parameters. For example, the W over L ratio of both transistors are not equal, or the threshold voltages of both transistors are not equal, or if the process parameter Kn prime is not equal. These can happen because of the variation in the fabrication process can also be different. So what happened is we have transistor parameters are different. So if the differential amplifier is not fully symmetric due to transistors parameters, then the mismatch in M1 and M2 creates mismatch in the transconductances GM1 and GM2. But we also know that AC current of transistors M1 and M2 are given as ID1 will equal to GM1 times VGS1, so that can be equal to GM1 times V common mode minus VP, where VP is the source, and ID2 will equal to GM2 times VGS2, which equals to GM2 times V common mode minus VP. So over here we said that the gates and the sources of both transistors are the same, but the transconductances are different. We also know that if we add the currents ID1 and ID2, that should be the same current going through the resistor RSS, so that will equal to VP over RSS. And we also know that ID1 plus ID2 will equal to GM1 plus GM2 times V common mode minus VP. That's basically by substituting for ID1 and ID2 in terms of GM1 and GM2. Then we can solve for VP, which is the voltage of the source, and the voltage of the source will equal to GM1 plus GM2 times RSS over GM1 plus GM2 times RSS plus 1 times the V common mode. Now we can solve for Vout1 and Vout2 to solve for Vout. Vout1 will equal to minus ID1 times RD. Keep in mind that this is the AC gain, so this will equal to minus GM1 times V common mode minus VP times RD. Then Vout1 will equal to minus GM times RD over GM1 plus GM2 times RSS plus 1 times V common mode. And Vout2 will equal to, by the same analogy, Vout2 will equal to minus GM2 times RD over GM1 plus GM2 times RSS plus 1 times the common mode voltage V common mode. And now what we can do is we can take the differences Vout2 minus Vout1 and divide by the common mode voltage. So we can say that the common mode gain is given as A common mode to equal to Vout2 minus Vout1 over V common mode, and that will equal to delta GM times RD over GM1 plus GM2 times RSS plus 1, where delta GM is the transconductances difference, which are GM2 minus GM1. Let's talk about common mode rejection ratio. First of all, it is industry standard, and it's defined as CMRR, common mode rejection ratio, is basically the differential gain, which is AD, or the common mode gain, which is ACM. The common mode rejection ratio can be expressed in dB as common mode rejection ratio in dB CMRR will equal to 20 log of AD over ACM, which equals to 20 log of AD minus 20 log of ACM. Keep that in mind. The common mode gain is undesired. We do not like to have a large common mode gain because it lowers from the quality of the actual signal. So what we like to see is a very large common mode rejection ratio. We would like to see the gain of the signal is very large compared to the common mode gain, or basically the common mode rejection ratio got to be as large as possible. The common mode rejection ratio in dB is defined as 20 log of AD over A common mode, or basically it will be 20 log of AD minus the 20 log of A common mode. Remember that when you take the log of two terms divided, you basically subtract the two logs. So that's what we have. Usually the common mode gain is bad, so we would like to make it as small as possible, or we like to make the common mode gain less than 1. Then this negative term becomes positive and the common mode rejection ratio approaches a large value. That is desired to make the common mode rejection ratio to be as large as possible, which means that we reject the common mode gain but we enhance the differential gain. So the common mode rejection ratio got to be as large as possible. So far we have discussed the differential amplifier and how does it amplify the differential signal, and how does the differential amplifier respond to the common mode input voltage. However, the differential amplifier that we have presented so far is unpractical, and the reason is the load resistors RD are so large and they cannot be used inside the IC chip. Basically, they are unpractical. So what we have to do is we have to develop another technique to implement the differential amplifier inside the IC chip, because this particular talk is about CMOS technology. So one of the ways to implement the differential amplifier is to use a differential amplifier with MOS loads, which means that the load resistors are replaced with transistors. So basically we use transistors that would act as resistors instead of RD. The reason is RD consumes large area of the chip. There are different types of active loads. Two are commonly used in practice. The first one is what we call diode connected loads. So basically, if you have a PMOS transistor, as the one shown here, we connect the gate to the drain, and this particular transistor behaves as a diode. We have discussed this particular connection early on in previous lectures. And the second type of loads is what we called biased load. So basically, the PMOS transistor shown here is biased at a particular voltage. And when you bias it at a particular voltage, this transistor The last circuit we will cover in this chapter is what we call differential amplifier with cascoded load. The cascoded circuit, as we discussed it in previous lectures, says that we will have very high gain. Because if you wanted to maximize the gain even higher, you can use cascoded amplifier. Basically, if you look at the circuit, the cascoded circuit, it's a little bit big circuit, but don't get scared. Let's look at it carefully. What you have here is the two transistors M1 and M2. M1 and M2 behave as current amplifiers. Basically, they will take the small differential voltage and they will give you large current through the drain. Then what we have is these two transistors, which are M3 and M4. M3 and M4 are biased at some particular voltage. We call it V plus 3, and these two transistors behave as voltage amplifiers. So basically they will take the current coming in from M1 and M2 and they will amplify it to a voltage at the output. So the type of amplifier here becomes common gate amplifier. Now the load has two stages. The first stage, which is M5 and M6, then the second stage, which is M7 and M8. All these transistors are properly biased at V bias 2 and V bias 1. We make sure that each transistor pair is perfectly matched. So M1 is the same as M2, M3 is the same as M4, M5 is the same as M6, and M7 is the same as M8 in terms of the W over L ratio and the design parameters and the number of fingers for each transistor when you do the 2D layout. Then we can also use the half circuit approach, and the half circuit will basically look like this. If you will see, the circuit starts from the top with M7, then M5, then M3, then M1, and we have the input voltage, which is half a differential input Vin over 2. Then we have the bias current, which is ISS over 2. So this is basically the half circuit, and the gain using the half circuit symmetry is given as AV equal to V out over Vin, and that is will equal to GM1 times GM3 times RO3 times RO1 in parallel with GM5 times RO5 times RO7. And it is obvious that this circuit will have a large gain because now you have much bigger output resistance than what we had before. The disadvantage is the cascoded amplifier requires large voltage overhead, and that will lead to a less output voltage swing range, and it utilizes large area, but the advantage is that it gives more gain. Now, something also you have to watch for is biasing the cascoded amplifier is challenging because you must guarantee that all transistors remain in the saturation region at all times. This particular circuit is a little bit tricky to design because in real world you have to also deal with the variation of the process parameters, how much the VDD changes. As VDD changes, all these transistors have to remain in saturation, how much the W over L changes due to the variation in the manufacturing parameters. As these variations change, you still have to make sure that all transistors remain in the saturation region, and then you still want to design the circuit to give you the maximum output voltage swing at V out and so forth, and it is a little bit challenging to design. Basically, this is the end of today's lecture, which is the differential amplifier. We discussed the basic differential amplifier, what does it do and how does it amplify the differential voltages. And that is very exciting because now we have actually looked at the input stage of the operational amplifier. Almost. The only thing we have to deal with in the next lecture is how to do the DC biasing. And once you understand how to do the DC biasing, you basically did the complete input stage of the differential amplifier. And this is exciting. So we are learning a lot of concepts, and they are very practical and they are useful, and some of us will carry with us to the job and to the field, and we will push and advance and implement new technologies as we continue, starting from today's lecture and beyond.